येतो ना तुम्हाला आवाज?
येतोय.
तुमच्या हे करावं होतं, व्हिडिओ बंद करून.
Hello. Chai ma'am, can you hear me? Am I audible?
Yes, sir. Yes, you are audible, sir. Sudarshan, sir, you are audible.
Okay, fine. Just let me know when to start.
Okay, sir. Sir, welcome, Sudarshan, sir, for this afternoon sessions for the FTP on emerging trends in deep learning and its application. So I'm Mrs. Dr. Chaya Jadhav, coordinator of the FTP. Welcome all of you, all the participants, for this afternoon session. I hope this session will be very informative.
Okay, good afternoon to all. Good afternoon to all, one and all. Warm welcome to AICD sponsored APDP on emerging trends in deep learning and its application, organized by Department of Computer Engineering, Dr. D.Y. Patil Institute of Technology, Pimpri. It's my great pleasure to introduce today's eminent speaker, Mr. Sudarshan Deshmukh sir. He is a founder, CEO, and AI researcher of deepinstitution.ai. He's completed his ME Computer from Bharati Vidyapit and BE Information Technology from Shivaji University. He is associated with different reputed organizations such as Birla Institute of Technology, Pilani, as adjunct faculty and visiting faculty in data science and AI at Symbiosis University. Also worked as head AI and data science at Demand Matrix and visiting researcher at University of Ottawa. He has also received different honors and awards as 2 US patents are granted into our file. He also having 3 national patents and nominee for IEEE TCPP Outstanding Service Award. He has published more than 25 papers in reputed journal and international conferences. He has also completed different certification as listed below: AI for everyone, deep learning specialization, sequence models, convolutional neural network, improving deep neural network and deep learning. He has also completed different projects in deep learning, deep convolutional network based face recognition system or home security system, neural style transfer using CNN, car detection for autonomous driving, customized music note generation using RNN, neural machine translation with attention, triggered word detection, Twitter sentimental analysis using EDA, AI-based solution for call center optimization of one of the top insurance aggregator. I just try to summarize your biodata and profile. So I just completed it. I request Sudarshan sir, please take a charge and continue the session.
Yeah, thank you, sir, for the introduction. So without wasting the time, let me share my presentation and then we will start with today's session. Yeah. Can you able to see this?
Yes, sir. Yes, sir.
Okay. So yeah, so the topic is deep learning, and we basically want to understand how deep learning is a better option if we compare deep learning with existing machine learning based approaches or rule based approaches. So rule based approaches are those approaches where we use traditional algorithms and then we try to solve the problem. And then if that problem is unsolvable, we would like to take help of machine learning so that using machine learning, we can able to approximate the non-linearities from that difficult problem statement. And then that difficult problem statement, we want to basically understand using machines. And then machine will derive some inference from that problem statement. So once that inference is taken out, machine can able to take an input and can able to predict some output. So this we can do with machine learning. And then slowly, if you see 2012 onwards, when Jeffrey Hinton, he published his research paper in 2012, popularly known as AlexNet. And from that paper onwards, people started exploring the possibilities and capabilities of deep learning. So what is there in deep learning, which is not there in algorithms, and along with that, which is not there in traditional machine learning algorithms. Okay, so keeping this objective, we would like to understand more about deep learning. I understood that in the previous sessions, you have learned the basic architecture of deep learning and the inner functionality of the neuron, and then different type of deep neural networks. Okay. So moreover, I will not try to repeat that, but let me give you one basic idea that when we are working with deep learning based architectures, the expectation is we should have structured input, and that structured input should be formulated under supervised setup. What does this mean? This means if, let us say, you want to give some images where there is a cat inside that image, and you want AI to understand or to classify, is there any cat in the image or not? Now, if you only collect the images and provide that to your neural network, it will predict something, but to rectify those predictions so that we can able to make sure that neural network with highest accuracy will predict whether there is cat in the image or not, we need to have supervised setup. That supervised setup is basically created by a human expert who is annotating the labels. And these labels are something 1 if there is a cat in the image, and 0 if there is no cat in the image. So this is the fundamental idea and the foremost requirement if you want to go with deep learning. So mostly deep learning is a supervised learning approach. It is not an unsupervised learning approach. Okay. Now, a lot of people, they always think and they always, adopt deep learning based solutions for any type of work. But there is a reason, and there should be some sound I would say, intuition behind applying deep learning based solutions. So when there is a problem statement given to you and you will be asked, can you please tell me that do you wish to go with deep learning or machine learning or rule-based approach? Then you should have some reasons so that you can make a decision across these three variables. So when to go towards deep learning? So there are two things. One is if you have huge amount of data with you, then you should go with the choice of deep learning. And along with that, when you have reasonable infrastructure at your hand, like cloud or GPUs, then and then only you will go towards deep learning for building your solution. So two deciding criteria. The first one is amount of data or volume of data which is available, and second is the infrastructure which you have. So if these two things you have, then you can go with deep learning based approaches. Okay, I am not going to repeat the architectures. Like there are a variety of neural network based architectures with deep neural network, shallow neural network, recurrent neural network, long short-term memory, convolutional neural network. So these are different type of architectures in deep learning which are used for different type of purposes. Like if you take standard neural network, it can be used for anything. If you use convolutional neural network, these are special purpose neural networks which are used to process images, because image is the high dimensional data, and processing high dimensional data with traditional standard neural network is computationally not viable solution. So a special purpose architecture is designed, which is called as convolutional neural network. Next type of architecture, which is recurrent neural network, which basically tries to process sequential data. So you can take, one use case where you are searching something in Google, and Google is trying to predict what can be the next word or what can be the next sentence when you are typing something in the text box. So those type of applications you can do. So recurrent neural network is a special type of neural network which understands the sequential embeddings or sequential dependencies of the words in the sentences. Okay, so there are a couple of more state-of-the-art architectures in market, but since this is introductory session and our focus is not that, so let us keep that part. Yeah. Right. Now, the basic understanding about neural network is there is a neuron, and these neurons are stacked across different layers to form deep neural network. So the function which is implemented inside the neuron is basically a logistic regression. So logistic regression is an algorithm which is coined in 18th century, and we are using this logistic regression as a base algorithm for our neural network. So every neuron in the neural network has two components. One component, the first half component, is taking the input and then multiplied with weight, and then some bias is added into that, which gives you Z. Activation function provides you some prediction. So I think till this point the topics are covered. Okay, but to make sure that why we want to do that, because all right, in every neuron we are taking the input, we are multiplying that with some weight, we are adding some bias, and after that we are processing that using some nonlinear activation functions. So there are a couple of nonlinear activation functions in the market, like sigmoid, tanh, ReLU, leaky ReLU, and many more. But what is use of this nonlinear function? Why we are using that? So basically, the intuition behind that is we are using deep learning for difficult, on difficult problems where finding some which is the relationship between input and output is a polynomial relationship with higher degree. So there can be a degree of 10, there can be a degree of 20, and then you will form a polynomial equation so that if you feed the input to the polynomial output, and then that predicted output is much, much closer to the ground truth. So you can imagine that the relationship between input and output is nonlinear. And to suffice that requirement, we are using these different nonlinear activation functions. Okay, so that's the purpose of using nonlinear activation. What is the purpose of weights and bias? Because if you see the first half of the neuron, what we are basically doing is we are multiplying the identity value of the input, which is x, with some w, which is nothing but weight. So these weights are initialized with some mechanism, and that value of weight is very, very small. So if you ask me about what is the deep learning, or how deep learning is capable of understanding complex relationships between input and output, it is through finding those weight matrices. Okay, so we call that term as a Jacobian matrix. So the fundamental idea of training to find Jacobian matrix, and that Jacobian matrix, if we applied onto identity value of an input, which is nothing but x, x1, x2, whatever those values are, then we will apply the weights in the Jacobian matrix onto those input values such that it will give us the classification or regression as output. So the purpose is to find the best value of W so that it will help us to filter some portion from the X. Let us say value of X is 1, for example, okay, and then we are applying a weight which is randomly initialized to 0.2. So when I implement 0.2 with 1, the output is 0.2, which means that the amount of information which I'm extracting from the identity function, which is X, is 20%. And if, let us say, you are giving an input, which is a cat image, and you want deep learning to understand whether there is cat in the image or not. So at the time of training, what deep learning is doing is it is changing the values of those weights such that it will find the best combination of weights, which if applied onto an image, there will be higher weights assigned to the portion where there is a cat, and negligible value or smaller values of weights are assigned to the portion where there is no cat. So this type of distribution of weights, if you want to understand, manually it's not possible, but using this deep neural networks, it's possible. Okay, and then once you randomly initialize these weights, initially, since it is random, you want to rectify or you want to modify these weights such that the predicted value will be much, much closer to the ground truth. So always ground truth is represented as 1 if there is a ground truth, and if there is absence of ground truth, we manually annotate that value as a 0. So when your neural network, after training, provides some prediction, you will get that predicted probability, and then you will compare, is that probability closer to the ground truth? Let us say, for example, that ground truth is 1, and your probability prediction is 0.3. So there is huge difference between 0.3 and 1. So you need something at the end. That something is nothing but your cost function. So you can use, negative log, and then you will calculate a sigmoid loss function, which will help you to calculate the difference between prediction and the actual, right? So once you calculate that loss for every sample which you are feeding to your neural network, you will sum that loss across all the samples in your training data, which results into your cost function. So that final cost, you are setting the objective, statistical point of view, to minimize that cost function. So if you want to minimize that cost function, which is nothing but the, you can say, how much your neural network deviates from the ground truth. Okay, so that is your cost function. And then what you will do is you will back propagate that value of the cost function. And then at every neuron, you are calculating the derivative, that how much each weight in each layer contributes towards a loss function. So partial derivative of loss with respect to the weight. Okay, so fundamentally, internally what is happening is, internally when you are back propagating that loss, we are calculating the impact of each W in each layer and in each neuron on the loss. Those who are impacting a lot, they will be modified a lot. Those who are impacting less, they will be modified less. This is what the derivative. And then the whole process will be conducted many times. And then somewhere after some number of epochs, you will reach to 90% or 95% accuracy. And beyond that, the increase in the accuracy is not possible. Okay, so the basic idea is this one, that we have introduced logistic regression so that the non-linearities or the non-linear relationship between input and output can be captured using deep neural network. Now, there are many activation functions, non-linear activation functions available in market. I hope this is covered previously, but the choice of these non-linear activation function is very much crucial when you practice these deep neural networks on real-time projects or on your PhD work, or let us say in industry. So when you take sigmoid, mostly sigmoid is used in first few early layers and last layer. If you take tanh, basically tanh comes somewhere near to the last few layers, and ReLU occupy the whole space from start to the end. So somewhere in the middle of the neural network. Okay. So how come these positioning of these nonlinear activation functions are decided? It comes from the practice. People try to randomly place these different nonlinear activation functions, and somehow they understood that if they position the nonlinear activation functions in this way, then they are getting better convergence. Okay. Now the question is, why we want to use nonlinear activation? As I said, the first reason is we want to understand the nonlinearity association between input and output. And the second most important reason, when you look into the stepwise operations which are executed from the first layer, from the source layer to the final layer, to the output layer, you will see that in every neuron we are performing three functions. The first part of neuron is multiplication and addition, that is W into X plus P. So there is one multiplication and one addition. And in the same neuron, the next half is you are applying sigmoid onto that Z, right? Now, when in every neuron, we are performing multiplication of some non-negative floating weight value with some integer data, okay, which is nothing but your input value. In every neuron, the multiplication scales your value exponentially, because multiplication is doubling something, right? So the factor of that doubling depends on by using which number you are multiplying that value. So you will use 5, then it gets scaled 5 times. So there is an exponential scale in the value. So if you don't use these nonlinear activation functions, what will happen is when you are propagating that multiplied input from one layer to the next layer, and in every layer it is scaled exponentially, there is high chance that the value of the output of the multiplication will be the huge number which these traditional architectures like von Neumann architectures, or I mean the traditional systems cannot able to store, because you can say that 64-bit systems, operating systems are there. So how much data these 64-bit operating systems can hold is 2 raised to 64. So if you imagine that you are stacking 100 layers one after the other, and in every layer, what is happening internally is multiplication, which is scaling it exponentially. Till 50th layer, you will come up with such a huge number which you cannot able to store. So it is needed to compress that number without losing the information between 0 and 1. And that's the basic aim of using activation function. The next important thing is how we are initializing the weights and biases. So the most important thing is weight, as far as you can say deep learning is concerned. Okay, because the better you initialize the weights, there is high chance that you will converge in minimum number of epochs or minimum number of training cycles. Now, is there any way to decide how to initialize the weights? Yes, there are ways, but those weights will not alleviate the requirement of training. So you need to initialize the weights with some understanding. So the first and most abstract way of initializing the weights is using some random sampling or some random initializers. And then you can give some limits that what should be the value of the weight. So you can give the limit as the weight should be between 0 to 0.5. So when you execute a random initializer, so for every entry of the weight, it will randomly sample the value between 0 and 0.5. Now, almost we are on track. So we initialize these weights, and then we started training. I mean, the training is something we multiplied those weights on the input layer. Okay, so you can understand that if I am initializing these weights to, let us say, 1, whatever is there, whatever is the input, I mean x1, the whole input I'm going to propagate towards output. If I initialize the value to 0.10 times 0.1, then the negligible portion of that x is going to get filtered towards the output. Okay, so the fact is, better we initialize the value, there is a chance that we will converge it in early number of cycles. So how to do that? So when we randomly initialize, and if there are many number of deep layers in your neural network, there can be a chance of exploding gradient, or there can be a chance of vanishing gradient. So if you initialize the values, I mean, you are giving a range between 0 to 0.5, and since there is a random sampling, let's say 80% of the weights are randomly sampled, which are closer to the 0.5. Okay, so in that situation, your weight values are, I mean, the magnitude of that weight is huge, 0.4, 0.45, 0.39, something like that. So that quantity is huge, which allows deep neural network to extract huge quantity from the input layer. So when you are forwarding huge quantity from the first layer itself, and in each layer, when you are multiplying that quantity with some W, there is high chance that towards higher layers, the magnitude of the value which is extracted from the earlier layers is huge, which results into, you can say, a derivative equals to 1. So when you got a huge value, which tends to get closer to 1, so when you calculate a derivative, right? So derivative with respect to 1 is 0, and derivative with respect to very small value is 1, right? So you can imagine that the huge value which you are taking, when you calculate the derivative, the graph, or the, you can say, the plot is almost horizontal. So there is no information available. So that is called as vanishing gradient problem. And if you initialize the weights to a very, very small value, which is extracting a small portion of input from the input layer, and when you calculate the derivative of the weights with respect to these very, very small numbers, it tends to approximately equals to 0. And no, it tends to approximately equals to 1, because the weights are also small and the value which is extracted is also small. So numerator and denominator are approximately same, which gives you a result which is 1, right? So mostly what will happen is when your derivative is 1, you will try to modify those weights onto larger front, right? So somehow the convergence will not be better. So there are, to solve this particular problem, there are weight initialization strategies available in the market, like HE initialization. So when you use HE initialization, what it does is it takes the weights, the dimensions of the weights in the next layer, and the dimensions of the weights in the current layer, and then you will divide that two vector, the multiplication of these two vectors with square root of 2, right? So that is the HE initialization. Sorry, the numerator is at, the numerator will be square root of 2, and the denominator will be mod of W1 and W2, the multiplication of both the magnitudes. So couple of strategies are available. The intuition of using these better initialization strategies is to come out from, you can say, vanishing gradient problem, and you can say the exploding gradient problem. So these two problems are there, and to avoid that, we supposed to initialize the weights at better value. Is there any way to initialize the weight? The bias? Initially, bias tends to 0. So it is the standard practice to initialize biases to 0. And then what you can do is slowly you will add the derivative of the partial derivative of bias with respect to weight into the 0. And then slowly the value of bias will get changed as you train your neural network to the next. Okay. Yeah. So these are some of the internal findings. As an architect of the solution, or as a researcher of the solution, you should know why rather than what to use, right? So everyone nowadays know that deep neural network is somewhere becoming popular and popular, and everyone wants to learn deep neural network. Everyone knows what is activation function. Everyone knows what is agent layer, input layer, and output layer. But rarely people understand that if this is the science, or this is the inner working of neural network, and this is the reason because of which we need to go and make changes in weights and biases and make changes in the nonlinear activation functions, then and then only you can able to provide optimal solutions. Now, yeah. So it's fine that we understood deep neural network, and then somehow you will be asked to use this deep neural network as a solution for your problem in hand. And let us say you do not have data, or you have just 10,000 images. For example, image we will take as an unstructured data, and these 10,000 images are available. So do you wish to use deep neural network as a solution? Answer to that is no. The reason being, with very small amount of data or small number of samples at hand, you cannot give enough opportunity to your neural network to understand the non-linearities across the data samples. Right? So deep neural networks are very, very data hungry, first thing. And second thing is, you cannot run your deep neural network, let us say having 10 deep neural network. It means skipping the output layer, or skipping the input layer, there will be 10 layers in your neural network. So, and in each layer, you can place around, let us say, 20 to 50 neurons. And you wish to run this architecture on a machine or on your laptop. What is the possibility that it will do the task in polynomial time? So polynomial time is just, you can say, in half an hour, for example. So it's not possible. So it needs a huge amount of computational power. So this type of tasks you should able to run on the cloud infrastructure or even on, you can say, GPUs, right? So this is the second requirement. Third requirement, you cannot provide inputs as is to the deep neural network. So you need to vectorize the inputs. So if you say that there is an image X and there is a girl in that image, let us take this example. Now, can you feed that image as it is to the deep neural network for processing? Answer to that is no. You need to vectorize that, because the image which is shown, as a human, I have that ability to see the image, okay? But how computers see that image is the collection of pixel values, okay? And this collection of pixel value is not one-dimensional vector, but it is a two-dimensional vector, because you can have X and Y dimensions of the image. And if the image is RGB, then there will be a third dimension, which is nothing but number of channels, which is nothing but red, green, and blue. So the first requirement is we need to pre-process the data. So how to pre-process the data is take each row and stack it vertically. Okay. So what I will do is I will first read the image using image package in the Python. So which will give me a grid. Let's say 64 by 64 is the image. And if it is color, it is 64 by 64 by 3, right? So how many pixels will be there? It will be 64 by 64 by 3. So that sums to around 12,288. Okay. So this will be the the total number of pixels available in the image. So you cannot feed this 64 by 64 by 3 as is to your neural network. What you're supposed to do is first vectorize that. So vectorization means what? Is you are converging a high dimensional representation into low dimensional representation, mostly n by 1, where n represents 12,288 for this example, and 1 is nothing but your column. Now, what you will do is you will apply some pre-processing, and in that pre-processing you will write some code. So that code will take first row and then stack that vertically. So 64 pixels in the first row, and you will align that vertically. Then you will take second row and you will place that second row below the first column. Okay, try to understand what I'm saying. So you are stacking each row vertically one after the other. This happens for first channel R. Then you will do that for G. Then you will do that for B. So this is R, G, and B in one single columnar vector. And the dimension of the columnar vector will be 12,288 by 1. Okay, and then so each entry in that vector is nothing but your X, which is nothing but the feature which you want to give to your deep neural network. Consuming that, deep neural network will try to understand the image. Okay. Now, if you see, so fundamentally, when the image is given to you in this three-dimensional form, image data, images are basically, they maintain spatial association. So what is spatial association? Spatial association is if there are hairs on the head, Below head, there will be eyebrows. Then there will be eyes. Then middle, there will be a nose. Below nose, there will be mouth. And some. So these are the traits. Okay. So this is called as spatial association. So the distance between ear and nose makes some sense if we want to understand, or if you want to recognize that object as a person, isn't it? So these are the spatial associations which are strongly maintained in the image. So if you see, as a result of vectorization, these spatial associations are fully relaxed. I mean, when you are taking the first row and stacking it vertically, when you are taking the second row and when you are stacking it vertically below the first one, the associations of these features gets diluted, okay? And then that vector you are passing as is to the neural network. So, uh, so let me give you one interesting fact that you can create one image where there will be a person, okay? And then again, you can try to uh, exchange some portions from that person's body randomly anywhere in the image. So there are two images. One is the image of the person without alteration, and the second is the image of the person where different portions of that images you change. So nose will be at the corner, head will be somewhere at the bottom, and something like that. Okay. And then you give the first image to deep neural network. Deep neural network will understand that yes, there is a person in the image. If you give the second image where you altered or exchange these different traits, and the association of these features is not maintained, okay, it is diluted. And if you feed that image to deep neural network, you will get something, unexpected. Still, your deep neural network will recognize that there is a person. How come this? This is because deep neural network understands the distributions and not the semantics. So in statistics, there is one separate branch which is called as frequentist analysis. So in frequentist analysis, what we basically try to do is we want to understand the probability distribution of each and every value for a given class. And for every class, let's say class, there is a cat, there is a person, there is a chair, there is a dog, right? For every class, there is some distribution of values which represents that class. And what deep neural network tries to understand is the probability distribution of those values with respect to the classes. And it is not capable of understanding the semantic associations. So if you take the head and if you place that, if you mark that head and place that as your legs, and you keep mark your legs and keep on your shoulder, still it will remember and it will recognize that as a person, which is a serious, I would say, flaw in the existing deep neural network. People are blindly, or since they don't know too much about this, they think that now there is something called as AI, and 90% of AI approaches are deep neural networks. It is going to solve any NP hard problem, right? But that's not true. There are some limitations because of which adopting deep neural network as a solution to every problem is something not possible. So that is one of the deficiency in the learning which deep neural networks has. If you would like to take this as your PhD topic, you are welcome. Try to find some maths which will try to link those associations with some weights, and if those associations are below these weights, you will not recognize that as a person. So different thoughts are there around that. Fine. Then the next thing about deep neural network is the hyperparameters. So people, many times they made some confusion between parameters and hyperparameters. So when we speak about hyperparameter and when we speak about parameter, there is a fundamental idea behind that. So something which change or affects the value of the output is parameter, and something which don't change or you can say don't affect the value of the output, then all those variables are called as hyperparameters. So what is hyperparameter? So learning rate is a hyperparameter. Okay. So when you will try to understand what is learning rate, you need to understand what is gradient descent. Okay. So gradient descent is basically a way in calculus which provides you a direction, and when you move in the negative direction of the direction which is given by gradient descent, you will reach to the local minima or global minima without exploring the whole solution space. I know that I'm using very, very difficult words, but this is the exact answer to that. Okay, so so let me give you one example so you will understand that. Yeah, so let us say you are moving around some hilly area and you throw a ball, right? So the ball will follow a direction where it will see steepest curve, okay? And then it will rest somewhere where that curve is horizontal. Now, when we draw a solution space, basically there will be too many, you can say, peak points and too many valleys. And in stats, these peak points are considered as, so if you draw this graph where your y-axis is cost, right, and x-axis is number of training cycles, your objective function is when you are training your neural network, you basically want to avoid those peaks because they are representing huge cost, and you basically want to go to those value locations, right, where the cost is minimum, right? And cost, we know that it is difference between your prediction and the actual. So how to do that? Because if you go with greedy approach, so greedy approach tends to see that every sub-solution in the given solution space should be tested and should be ranked as per the value, and then you will rank those in the ascending order, and you will pick the first entry in that rank, which is nothing but the subsample for which you got the least cost. Now, these problems are not simple problems. That's why we are using deep neural network. Okay. Since your solution space is huge enough in n dimensions, you can imagine that how many subsamples are available in that solution space is, let's say, 10,000, which is so small. Practically, it should be in millions and billions. But for the sake of academic understanding, I am keeping that to, let us say, 10,000. Now, I want to sort these all samples, sub-solutions in ascending order, right? So to sort that in ascending order, what I need to do is I need to pick the one first, and then I need to make n-1 comparisons. Then I will pick 2, then I will make n-2 comparisons. Then I will pick 3, and then I will make n-4 comparisons. So when you will take this chain, and when you want to normalize that, it equals to n factorial. Okay. So n factorial, if let us say you have n equals to 10,000, which is a very, very small number. Okay. I mean, 10,000 solutions you have, and out of these 10,000 solutions, you want to pick the one which is best. It's the objective function. Then 10,000 factorial will be your solution space of these total number of combinations you will have at hand. And then from all these 10,000 factorial combinations, you will pick the combination where the first entry will be the least and the last entry will be the max. Imagine even today's supercomputers are failing at processing 1,000 factorial, and processing 10,000 factorial is still in the imagination, and probably that should be the reason because of which Google, Microsoft, IBM, they are pouring a lot of money in incubating quantum computers. Okay, so this is also a flaw in deep neural networks. So fundamentally, it's not possible. So what is possible is just use one approach which is called as gradient descent, which for every back propagation, it will provide you some intuition about the direction, which if followed, most probably you will get better accuracy than the one which you got previously. Okay, that too without I will say visiting every solution in the solution space. Okay, so yeah, so that's the purpose of using the gradient descent. See, if I went deeper and deeper in these all things, there are a lot of questions, not many questions you will have. But let me give you some fair idea at a very abstract level. Still, I am not discussing these all things in detail. Okay, so this is a gradient descent. So let us say when you pick your weights randomly, what happens is with that weight, you will get some prediction, right? And then you will calculate the cost function, which is nothing but difference between your ground truth and the prediction. And then that you will plot. So that cost you will plot onto this XY plane where your Y is basically a cost and your X is basically the number of training cycles. Now that point gets located randomly on that XY plane somewhere. And your objective function is to go to near to the x-axis where the value of y is near to 0. Okay, so you can imagine a hyperbola. Okay, somewhere you are at some point where y is 0.8. I mean the cost is 0.8, and you want to go to the point where your y is 0.1. I mean the cost is 0.1. Now you are at that 0.8 position, but you don't know how to go to that 0.1, right? So in every back propagation, for initial few thousand number of cycles, deep neural network internally, it randomly try different weights. It's go on trying different weights, this weight combination, this weight combination, this weight combination, this weight combination. Somewhere when it tends to use the number of combinations, and along that path, it tries to understand one hypothesis. Okay, and that hypothesis is, if I'm making the changes in these weights, and if I'm increasing some weights and decreasing some weights, it has positive impact on the error, right? It means my error is reducing. So that's the direction you got internally with the gradient descent. And then that gradient descent allows you to follow the same hypothesis. May not be true after a couple of number of training cycles, but it will remain true to some extent, right? And then you will exchange your hypothesis, and then these sequences of different hypotheses leads you from the 0.8 position to a 0.1 position on the given XY dimensional plane. Okay. Now, so when you want to move from that 0.8 position to 0.1 position, you can take a step size. Let us say you will move by 0.1, 0.1, 0.1, 0.1. So it will take huge amount of time, right? So you need to decide some threshold such that you will compare the previous cost function and current cost function. And if the current cost function is lesser than the previous cost function, you will try to follow the same hypothesis, which allows you to get the current cost function. Now, after how much time you want to do this assessment, this is nothing but your learning. So learning rate, basically in industry, what we do is we use adaptive learning rate based policy, where we calculate the gradient, and if that gradient is very high, then learning rate is very small, and if that gradient tends to near the zero, then we increase the learning rate. So you can imagine the situation that if the curve is steepest, then please take small step, because if you take big step, there is a chance that you will fail. And when you came to somewhere, 50 degree or 60 degree or 70 degree plane, it's somewhere almost near to the horizontal. You can take bigger step sizes to reach to the global minimum, right? So this is the whole thing which is implemented when we decide the learning rate. Now the second hyperparameter is the iterations. Okay, so the number of iterations is how many number of times you want to train your neural network. Hidden layers is nothing but how many number of layers you are stacking in between. Hidden units in each layer, how many number of neurons you are placing. Choice of activation function, again, you know these activation functions. Then momentum is again one more concept which adds pace to your flow. So basically you want to reach to the global minima on that XY plane. So how fastly you can go towards that. Okay. So in the existing maths, when we devise gradient descent, there is no alpha factor available, which adds some magnitude, which increases the pace or speed of the step size. Okay. So that alpha factor, which introduces speed into the gradient descent, will make you the momentum. So if you increase the momentum, it helps you to reach to the global minimum in minimum time. Okay, so that's the momentum. Next hyperparameter is mini batch size. So yeah, so yes, so batch normalization is one of the idea which subsequently introduced when people started facing problems of overfitting. Okay, so I don't know whether you are aware with overfitting or underfitting these ideas. I mean, high variance, high bias, low variance, and low bias. Okay, these are some of the ideas which basically, as an architect of the solution, helps you to understand where what is going wrong. So when there is a high variance, it means my architecture is not generalizing well. So you are having better accuracy on your training data, and you are not getting that much of accuracy on the test data. So it fails to achieve the same accuracy. That's called as high variance. And high bias is a case where at the training time only, you don't get better accuracy. That's the high bias. So mini batch size. So what should be the size of your batch is also an hyperparameter which basically helps you to avoid the case of high variance. So if you avoid that case, your model will generalize well on the test data. Okay, so this is one idea behind Mismatch. Second idea is, let's say you are having a training data, and let's say the number of training samples is 10,000. So when you are going to calculate the cost function, so for every sample, you are calculating I will say the error, and then sum of all those losses across 10,000. If I take average across those 10,000 samples, it is a cost function. So fundamentally what I'm doing is I'm calculating the cost function for the whole training data set. And then that cost function I'm providing as an input to the backpropagation. And backpropagation is a process where we are trying to modify the weights such that it will help us to minimize the difference between prediction and the ground truth. That's the reason behind that. You can imagine that for every 10,000 you are doing that. What if you do that for every 100? It gives more number of chances to your deep neural network to modify itself for a single iteration of training cycle. It means 10,000 divided by 100 is 100. So the number of times you are going to modify the weights is 100 just for one single feed of the training data, where earlier it was only once. Imagine a situation that it basically helps the neural network to make the modifications in the weights lot many times, and that gives neural network more number of opportunities to tune itself with the variances which distributed across the sample space in the given data, right? So that's what the mini batch gradient is. Now there are a lot of problems because it's not that much simple that we are just keeping the batch size to 100 and then we are giving more opportunities to tune the deep neural network. What if the distribution of these different batches differ or they are different than one another? So if the distribution of these samples which are present in every 100 size batch, if they are different, then it provides shaky behavior to your neural network. I mean, you will imagine a graph where y is cost and the x is number of training cycles. So when you plot a behavioral graph in this situation, it will be a zigzag manner, full zigzag, and you will not see any smoothened behavior of that graph. And the more the zigzag way, the more time it will take to reach to the local minimum. So, so the first solution to that is you can, rather than picking the batches sequentially, like first 100, like 1 to 100, 101 to 200, 201 to 300, rather than doing that, you can apply random sampling without replacement, and then you can pick those 100, 100, 100 ka batch, and then you can feed. To some extent, you can avoid that zigzag manner, but not fully. You can resolve that, and then right. So if you want to get rid of this particular situation, what you can do is when you are defining deep neural network architecture, you can define a batch normalization layer after odd number of hidden layers, so that the batch normalization layer basically applies normalization and standardization, using which it transformed the subspace such that if you calculate that distribution, it will result into zero mean and unit standard deviation. Okay, right. So that helps you to relax those discrepancies across the distributions of the batches, and then most probably you will converge well when you are plotting the graph cost versus number of training cycles. And the last one is the regularization, which is the most important hyperparameter. So there are L1 regularization, L2 regularization, and many more. But most popular is L2 regularization. So yes, so what is L1 and L2? So when you take a single norm of the weight, it is L1 regularization, and when you take squared norm of a weight, it is L2 regularization. So when you take L1 regularization, it basically calculates the derivative only once, and when you take L2 regularization, it calculates double derivative. I mean, the prime one derivative, partial derivative of, let's say, y hat with respect to w, and then partial derivative of w prime with respect to w double prime. So rather than getting into maths, let me tell you what is happening is when you calculate the derivative, L1 derivative, there is a high chance that the resultant Jacobian matrix, the weight matrix, will be more sparse, because L1 tends to create the values of the weights which are much closer to the zero value. Hence, the output matrix is sparser matrix, but L2 regularization don't do that. It will not push the values of the derivatives too much closer to zero. Hence, the matrix will not be sparse. It will be more denser, and then this denser matrix will help you to get the values, or to filter the values from the input and feed those values to the hidden layers in between, and hence it will result into better generalization. Okay, so this is also a hyperparameter which you need to tune. Now, who is going to do that? So this is the task of a data scientist, because in deep neural network, in machine learning, these models are doing their learning on their own. So if you see today's market, data scientists, ML leaders, these are the positions which are highly paid. Okay, so why organizations are paying it? I mean, comparatively high, if we compare in the market the other positions, it is because those are the people who know the intricacies of tuning the hyperparameters, setting up the environment, and optimizing the, the training processes and all the other things. Okay, so these are the hyperparameters, and this is the only task which humans do. The rest of the things are done by our deep neural network. Okay. All right. Now, as we understand this, it's very important to set up your ML app or DL app. So there is a difference in machine learning and deep learning. So that difference is, let us say you are given with 10,000 samples, okay, and you have used a decision tree, or let us say support vector machine, as your machine learning algorithm to process that, to perform classification or regression. Okay, now there should be one decision about how I'm going to partition the data set. So there will be three things. One is training, one is development, and third is test. Okay, so training partition is used to train the model. Then the development data set is used to evaluate the model, and the test data set is used to test the model. Now, what is meaning of this? So when I'm using the word evaluate, what I'm trying to say is I want to check whether my model learned something in the training and what is the extent of that learning. If the extent of that learning is very, very poor, then I should again retrain my model. Okay. Then again, I will train that model on some more number of data samples. And again, I will go to the development stage. So basically what I'm doing is I'm evaluating the learning. And once I got enough accuracy on evaluation, I'm going to test that model. So, uh, so if it is traditional machine learning, what you can do is 6,000 samples you can keep for training, 2,000 for development, and 2,000 for testing. What if I'm going to use deep learning? Should I follow the same distribution? Answer to that is no. The distribution should be around 98% into training, 1% into development, and 1% into test. Now the question is why? First answer to this question is because your deep neural network architecture is data hungry, and you are not allowing that neural network to learn a lot if you keep the distribution 60%. But when you keep it 98%, you are giving enough opportunity to learn, and 1% for 1% of the 10,000 is still 100. So 100, though it looks small, but it's enough for evaluating, and 100 is good for testing, and remaining 9,800 is used for training. Okay, if this is, let us not take 10,000 as example. Let us take 1 million as example. In this case, I will keep distribution to 98, 1 and 1. And if I have 10,000, then I will keep this distribution to 80, 15 and 5. So it's totally, I mean, this is your factor based on how many number of examples you have to train. Okay, so this is one thing which makes the difference between classical ML and deep neural network. Second important thing is we need to understand what is bias and variance, because bias in standard term is a situation when model did not understand or learn anything enough from the training data set is a high bias. High variance is model learned so much from the training data set that it looks like model remembered everything, is high variance, which we call as overfitting. And what is the just right condition is something which is shown in the graph, the middle one. Okay, so that function is not straight and not too much nonlinear, but something in between, which partitions enough number of samples into their own classes. Okay, so this is just right. Number point of view, when we want to understand that how to classify a particular situation into a given case. Let us take example that in training you got 1% error, and in test you got 11% error. It means model is not able to apply the knowledge which it learned in the training into test. Right? It means model is overfitting, which is nothing but high variance. If you have 15% error in train, for example, and 16% error in test, there is high bias because error is high in the train, right? But it will not be high variance because the difference between train error and test error is very, very small. It means that model is generalizing well. If you got train error 15% and test error 30%, training error is high, that's why high bias. Difference between train and test error is high, that's why it is high variance. So both are there. Okay. And let us say if you got 0.5 training error and 1% test error, then that will be a situation which we would like to expect, that we want this condition as achievable condition, right? So how you will check? So when you train your deep neural network, you will first check whether it results into high bias. If answer to that is yes, then the solution is increase the number of samples in your training data set so that your model will receive enough knowledge and enough information so that that bias condition will be resolved. If high bias case is resolved, then you will go for high variance. So if there is a case of high variance, then what you will do is you will try to basically apply some strategies like hyperparameter tuning, giving more data in the training, then applying some regularization techniques, and then if nothing is working with these existing approaches, you will altogether use some different architecture which will resolve the high variance case. And if answer to both, that is high variance and high bias, if you got answer to these two questions as no, then you are done. I mean, you come up with a model which generalizes well and which learns mostly enough inference from the training data. Okay, this is how you can set up your deep neural network application. Now there are two things. Let us say you are at high variance case. So how to reduce or avoid this case of high variance? High variance, popularly called as uh, high variance is popularly called as overfitting. Okay, and high bias popularly called as underfitting. So how to prevent this overfitting condition? So there are a couple of techniques. The first technique is regularization. Second technique is dropout. Third technique is data augmentation. And fourth technique is early stopping. So the first technique is L2 regularization, where you will see that what we did is we added the squared norm of weight. So you can see that the cost function j of w comma b is equals to 1 by m sum over 1 to m y log y hat plus 1 minus y log 1 minus y hat. This is the sigmoid error. I mean, the loss y hat comma y is when I expand, it looks like 1 by m summation over all m 1 y log y hat plus 1 minus y log 1 minus y hat. So this is the sigmoid cost function. And then into that cost function, we are adding lambda divided by 2m, the square norm of the weights. Okay? So what it basically does is it normalizes the fluctuations in the values of the weights, which linearizes the inference channel which gets established between input and output. So internally, when you plot how the branches or the neurons gets activated when you place this extra factor of L2 regularization into the cost function, you will see moreover linear flow of the information from input to output. So it basically it smoothened the way weights are changing as per the back propagation derivative which is supplied to it. Okay. That's how we are using this regularization. And since we are somehow converging the non-linear flow into more linear flow, it reduces the idea of I mean, it reduces the idea of high variance, right? And it converges that too much complex function into more linear function, which helps to regularize the overfitting condition. This is the first idea. The second idea, or the second solution, which is more simple, that solution is using dropout. So, so the dropout, what it says that randomly switch off some of the neurons in each hidden layer. So what does that mean? So let's say if I keep dropout equals 2.2, it means keep 80% neurons on and shut down 20% neurons in each hidden layer, that too randomly. Okay, so for every epoch, this dropout will be activated, where these neurons are shut down randomly. Okay, so now if someone wants to understand how it will help to reduce the overfitting condition, so you can imagine that there is one X1 and there are 5 layers. Only X1 I'm saying in the input layer, and in these 5 hidden layers there are 5 uh, neurons. So that X1 gets propagated through every neuron in the first layer to every other neuron in the second layer. So how many different ways are there using which X1 in the input layer is propagating to the output? So you can imagine 5, 5, 5, 5. So there will be 20 neurons, and again this one neuron which is 5. So 20 factorial plus 5. And again for the output, it's one output layer, one single neuron, right? So it will be 10. So 20 factorial plus 10 will be the total number of paths which are available to you, using which that X is propagated from input layer to the output layer. Okay, something amazing. So if you have these many number of choices available, obviously there is a chance that you are learning a lot, which tends to looks like you are remembering everything. Okay, so to avoid that, what you are doing is you are switch down the neurons randomly. That number should not be very high. It should be max to max 20%. Starting from 5% to 20%, you can set that number to any number. So it will try to reduce those number of channels or the paths, activated paths from input output. So you will get only few paths. And the second thing is the number of times your value of X is processed, which is introducing the non-linearity, because once it is processed, you are applying nonlinear activation function onto that. By switching down those neurons, you are reducing those non-linearities. So that is also one extra advantage you will have when you want to go with the drop. This is second, right? So indirectly, when you look into this particular case, it looks more linear by fashion. Okay? This you can do using dropout, but make sure that when you are using batch normalization, or when you are using uh, uh, yeah, so yeah, so when you are using batch normalization, make sure that dropout should not be used, or vice versa. Okay, so this is one more thing. The second way of preventing overfitting is using data augmentation. Now, why there is overfitting? Because my model did not generalize well on the test data. One of the reason might be the distribution of the test data with the trained data does not match. So if it is not matching, I should make sure that I am creating enough samples in the training data which helps me to match the distribution in the test data. Okay, so that you can do by assuming this case. You can use data augmentation as a technique where you can take a single image in the trained data and you can apply different type of transformations, scaling, alterations on the image so that multiple number of samples from one single image you can create, and that adds enough variance in your training data. That can be done using data augmentation. Okay, so this is also one of the effective technique. Mostly people follow this data augmentation technique as a de facto standard when they work on the, the convolutional neural network or image network. That is one. And the third, or the maybe it's not third, the fourth one is early stopping. Now, if you see the graph, you can see that there is a y-axis and there is x-axis. And what you are doing is you are basically recording the cost function for every iteration. All right. So when you will see that in every iteration you are recording the cost function. So there are two lines, two functions. One is red and one is black. So when you see the black function, there the training error is basically reducing. Okay, as you increase the number of iterations, the training error gets reduced. And when you plot the development error, okay, so that development error after some number of iterations is increasing. Now, what is overfitting is your model is not generalizing well. It means there is a difference, high difference between trained and test or development error. Okay, so what you can do is you can plot this graph, and for every recording of train and evaluation, okay, you are calculating the difference, and you will find some point where the difference between these two errors started increasing, and that point you will stop your training so that the difference between training error and evaluation error will be minimum, and then you can able to avoid the, I would say, overfitting condition. Okay. So this is something you can use to optimize the performance of your neural network. It's very important to understand these techniques rather than knowing the deep neural networks, how to train, and what all basic terminologies available in the deep neural. Okay. Let me, okay, so 3, just we had 1.5 hours done. So if you have any questions, Chaya madam, you go ahead and ask the questions in between, or should we take the question at the end? I think she's on mute. Participants, what you are expecting? Should we take the questions at the end, or should we take the questions in between? Chaya ma'am, you are on mute. I don't know if she is attending or not. Okay, all right. So let us take the questions at the end rather than taking it in between. Fine. So this is how we are. Just This is how we are preventing the overfitting. The next thing is how to optimize the deep neural networks. Okay, so there are a couple of ways to optimize the deep neural network. Mostly, the way which is followed by people is they first try to normalize the inputs. Normalization and standardization are two techniques which we use as a pre-processing techniques on the input data. So when we normalize the data, what we do is we calculate average of the data, which is nothing but your mean, and then we calculate the standard deviation, and we want that standard deviation equals to a unit value, which is nothing but 1. So mean, so when you normalize the input, the output of normalization is a data distribution with zero mean and unit standard deviation. Then we can say that that particular input is normalized. If you don't normalize, there is a chance that there are some portions. So when you plot the data, there are some denser areas, there are some sparser areas. So this type of data is not good fit when you want to feed that to train your neural network. Okay. So the good fit is the perfectly balanced data where the mean, I mean the center of the Cartesian space should be near to the mean of the data distribution, and the standard deviation should be unit. So this is one of the way to optimize your training. So there is almost 100% chance that when you train your deep neural network on normalized input, you will converge well at the end. Okay, so this is the first thing. Then we need to deal well with two problems. One is vanishing gradient and is exploding gradient. So to deal with that, we need to initialize our weights, and you can initialize those weights using some initialization techniques which are known in the market. One is HE initialization and second is Xavier initialization. So how you will initialize the weights is you will take n, which is nothing but the total number of neurons in the hidden layer. Okay, that will be n, and then you will basically take 1 upon n raised to b. Okay, and then you will calculate square root of that. So this is how you will get the sample seed point to initialize your number. Okay, so if you apply Xavier initialization rather than random initialization for your weights, there is high chance that you will avoid vanishing gradient problem and exploding gradient problem, which is because of the result of the exponential increase of the values as a result of weights and input multiplication. That is also one of the way to optimize your training process. Second, one of the important technique to optimize your training process is perform gradient checking. So for every backdrop, when you are calculating the gradient, so what is basically a gradient? So gradient in regular mathematics term, it is derivative. Okay, and when I will calculate derivative of x-axis, it is 0, and when I calculate derivative of y-axis, it is 1, and something in between, okay, 45 angle or 30 angle, it is between 0 and 1. What deep neural network expect is derivative should always be greater than 0 and should be lesser than or equal to 1. Okay, so in gradient checking, you will be checking for every backdrop that whether your gradient, which you are calculating for every hidden layer, is between 0 and 1. And if answer to that is yes, go ahead and apply the training process. The time when your gradient equals to 0, which says that there is nothing to learn in the data, right? Then you can stop. When your gradient is somewhere near to 1, there it means that there is everything to learn, which means that you need to extend your training cycles to more numbers. Okay, so this is how you will set up your infrastructure, your experiments, your architecture, and this is how you will set these tuners so that you can able to optimize your training process. Okay, now the other thing about optimizing deep neural network is we have to use mini-match gradient descent. Okay, so there are a couple of ways. I mean, one is stochastic gradient descent, second is mini-batch gradient descent, and third is standard gradient descent. Okay, so the difference between these is in case of stochastic gradient descent, for every input, what you are doing is you are calculating the cost, and then you are changing the weights as a result of backpropagation. And then once those things are done, you are feeding the next sample, okay, in the training cycle. This is stochastic. Standard gradient descent is you will feed all the samples in the training data. You will calculate loss function for every sample. You will take average of the loss across all the samples in the training data, and then that average cost function you will feed back using backpropagation. Okay, that is, I would say, gradient descent, standard gradient descent. And something which is mini batch gradient descent, you are not taking sample size as 1 or sample size as n, but you are taking sample size something in between, which is, let's say, 100, and then you are calculating the cost for every 100. So if you see uh, the graph for standard gradient descent is more smoother. You can see that graph where the function is smoothly decreased if you increase the number of iterations, but it takes more time because for every 100, for every n you need to do that. In mini batch, what you do, in stochastic, what you do is you do that for every sample. So the spikes are huge, ups and downs are huge because every sample you are calculating the cost. And computationally, it's not a good way to do that. And the third way is mini batch gradient descent, where you are keeping some reasonable size, 100 or 200, if the n is 10,000, and then you are calculating that. So you will reach to the local minimum very fast, faster than the stochastic, and the time which is taken using mini batch gradient descent is also lesser if you compare that with standard gradient descent. So time perspective point of view, when you are training deep neural networks 1,000 number of times, these small improvements makes more sense. So this is one way to optimize. Okay. Then second way of optimizing these algorithms is make some modifications in the gradient descents and introduce momentum into that. Okay. So momentum is a magnitude which allows you to take higher step size that is based on the gradient slope. So if the gradient slope is smaller, then you can take higher step size, and the gradient slope is higher, then you can take smaller step size. Okay, so this is introduced by adding some beta factor, and that is nothing but gradient descent with momentum. Again, it will reduce some time to reach to the local minimum. And again, one more improvement in the gradient descent with momentum is RMS prop, root mean square. So what we are doing is just we are root mean squaring the weights, and that helps to reduce the fluctuations in the given WB space. Okay, so using root mean square operation, we reduce those fluctuations to a more smoother fluctuations, which allows us to converge well. So this is also one way of optimizing the deep neural network. The one which is mostly used by everyone nowadays when they want to optimize deep neural network is ADAM optimization, which is the good points of momentum, gradient descent momentum, and I mean the pace, and the good point from RMS prop is to smoothening those fluctuations. These two are taken together, and the combo of these two is nothing but your ADAM optimizer. Okay, so mostly when you want to optimize your algorithm, you want to minimize your cost function, that too in minimum number of cycles. That is achieved using ADAM optimization as a de facto standard. Nowadays, again, one more new thing is coming in optimizing these deep neural networks is learning rate decay. So decay the learning rate based on something. Okay, so what is that something? So learning rate is nothing but at the step size at which we want to evaluate the performance, the error, and then we want to compare that with the previous step size. And then if it is lesser, we want to go on the same direction. Okay, this is learning, isn't it? Same. I mean, in the human terminology also, we are using learning means what? Something we learn, if it helps us that, yes, this helps me to learn, we go in the same direction to learn more. That is the case. So when you will take this step size, and if you take the constant step size, as you go towards the local minima, there is a chance that because of the slopy nature near to the local minima, when the error function is very, very small, you may skip that local minima if you use the fixed learning rate. Okay, this is first point. And the second point is, if you're using fixed learning rate, there is high chance that you are not taking into account the gradient of the error with respect to the weight. Okay, so to avoid these 2 points, what people started adopting is based on the gradient, they will reduce the learning rate. So moreover, learning rate will be higher when your slope is non-linear, and I mean slope is vertical. Okay, and when your slope started becoming horizontal, your learning rate becomes small, so that mostly you could able to meet the local minima where the error is this small. Okay, so these are some of the optimization approaches which are available in the market. Now, when you optimized the approach, the algorithm, the deep neural network, still you are not getting the performance. Okay, then you should start with tuning the hyperparameters. So which hyperparameters are there? Couple of hyperparameters we already have discussed. So what should be the flow? What should be the importance? So which hyperparameter I should take on priority, which has higher impact on optimization? So this is the list. So the most important hyperparameter to tune is learning rate. After that, number of hidden units, number of neurons in the hidden layer. After that, what is your mini batch size? After that, your momentum which you takes, then number of hidden layers, and then learning rate decay. Okay, so this should be the priority index supposed to be followed if we want to optimize the performance of the architecture. Okay, all right. So when you would like to infer something, okay, from the given solution space, let's say in case of classical machine learning problems, what these machine learning models do is they applied some grid search, okay, And in that grid search, they will try to attempt mostly every solution, sub-solution, and then they want to pick the one which is best. But in deep neural network, we don't follow this type of policy. The reason being the huge sample space which is available. Okay, so what we want to do is we want to basically uh, take some random sampling, or we want to pick some random area, and from that area as a starting seed point, we want to check where we can get the optimal solution blindly. Okay, and through a brute force approach, we can able to achieve that by chance, and that by chance can be converged to more deterministic way by improving the hyperparameters, by setting some optimizations, and by increasing the number of training cycles. So moreover, that brute force approach, which helps you to get the optimal solution by chance, can be converged into a deterministic approach where you know where is the solution is achievable through this optimization and hyperparameter tuning. Okay, so yeah, this is what is all about when we do hyperparameter. Okay. Now the next one. Now once we understood that these hyperparameters and everything are tuned, and we set up correct architecture for our problem statement in hand. Now our goal is to structure our deep learning projects. So how to structure deep learning project? One is setting up the goal, right? So the goal is how much accuracy you want. So let us say you will say that I am expecting 98% of accuracy, okay, which everybody is expecting, which is wrong. So the correct way of assessing that what should be our goal is take two things. One is Turing test and second is Bayesian benchmark. So Turing test and Bayesian benchmark are the proven ways to know what is maximally possible to a human expert. So let us take example that you want to develop a deep learning solution for detecting tumors in the X-ray images. Okay. Now you have 10,000 such images where in some images there is a tumor and in some images there is no tumor. And your PhD guide set up the objective function that we want 99% accuracy. Okay, so is it correct? We will try to get final concluding remark on this once I cover the next part. Okay. So what I will do is I will take these 1,000 images and we'll go to a radiologist who has proven experience, let's say, of 20 plus years, and then we'll give him this, and then we'll ask him, can you please tell me that how many images are there where there is a tumor and the remaining where there is no tumor? So let us say you have the ground truth already with you that out of 1,000 images, 600 images there are tumors and 400 images there are no tumors. And what that person told you after going through each and every image, that there are, let us say, 500 images where there are tumors and there are 500 images where there is no tumor. Okay, so the false positive is number of false positives are very high in this case. But you can set up a hypothesis that something which the human intelligence can able to achieve is, let us say, 90%. Why I should expect my deep neural network to give as 99%? So you should set up your Bayesian benchmark to 90%. And you should compare your performance to that 90% as 100%. So I will keep that 90% as 100%. And then if my neural network, deep neural network predicts with the 90% error rate, then, I mean, 90% error rate, I'm saying, 90% accuracy, it's 100%. And if it is giving 80%, then it's 90%. So the relative margin, if you see, it's just 10% between what Bayesian benchmark is recommending and what is achieved by deep neural network. Okay, so this is how you should set up your goal. Once you set up your goal, you need to set up your development and test sets. It's very important if you want to achieve the best performance. You should not open up test set in any chance, because if you provide access to your trained model, a test set, it will be visible to the model, and then model already know that what will be my test set, and then the human expert will try to make the modifications of the model so that he will try to moreover tune the model towards the test data set, and you will get highest accuracy on the test data set, which is not something practical, right? It happened because it happened because humans are given access to the test data set. So in industry, we follow a practice where we don't allow a single point access of any test data set. Okay. So we allow data scientists to get the train and get the validation. And the time when we submit the model to us, even we also don't see the test data set, and we directly see the performance of the model. Okay. So that much of care you need to make sure that your test data set should be so much secured. Okay. This is about, setting up the environment for development and test set. The other thing which is more crucial when you are setting up the environment. Okay. Let me check. Oh, fine. So the other information about setting up the development and test set is, am I more concerned about the distributions? So let me give you one example so that you will understand. One fine day, let us say, what you did is you completed your PhD in deep learning, and that day you told your wife or your husband that today I completed my deep learning, completed my PhD in deep learning, and now I'm very, very happy. So, your husband, he told you that that's really great. Can we build one deep learning app for simple application, because we have a cat in our house? So let us build one small app. We will install that app, and I want to check your knowledge that when I will use that app and when I will click the photo, it should say that there is a cat. Okay. So you said that yes, that's perfectly all right. I know everything in this now, and let us build that app. So what you did is you collected the images, cat images from the internet, because you want to make sure to make your husband or wife very, very happy that you know deep learning. You collected around 50,000 cat images from the internet, and then you take 100 deep neural network, the convolutional neural network, and then you trained it using optimization and using everything, right? So you got 99% accuracy, and then you deploy that app. You use some UI UX technique like React.js and something, Node.js, and then you build app, and then you launch that. And you took around 10 days to do that. And after that, you came to home and you told your wife that, hey, I developed this deep learning application. Can you please download from your Play Store and use that? So she downloaded that, she installed that, and there was cat in the house sitting on the table, and your wife took the picture. And the time when she took the picture, immediately the label which was shown is there is no cat in the image. Then she thought that it's enough. You did enough. You wasted your enough time in PhD, and still you are not able to achieve the performance. You should help me in the kitchen now. So this is the regular scenario in deep learning. I'm not joking. This is how things are working. So you thought that, yeah, this is something I was not expecting, and why it has happened, right? So when you asked it to someone who is expert, really expert into that, he will give you the answer like this. So the answer is when you selected your images, those images were picked from internet, which are pre-processed high-dimensional images, which are processed such that it will give better appearance and better customer satisfaction. Okay, but you train your model onto those type of images, and now the test image is something which you have taken from your home. The camera is, let's say, 10 megapixel. The environment is at your home, and the most riskiest part is when you collect those cat images online. Mostly those cats are from US or some developed countries. They are fat cats and developed cats. Okay, our cats are, they are slim and trim type of cats. So a lot of changes are there, distribution perspective point of view, which uh, most probably are the reasons which failed your deep recognition app. So the point of concern in this case is how you are picking your development and test set is very, very important. Okay. So when you are picking your data from US, UK, and Europe, and you are applying that data in India, it's of no use. Another example for that is sometime back I heard that Tesla is going to start their operations in India by 2021. So the Tesla, the basic model, how the Tesla car is developed is in the front portion of the car, they basically kept the computers, and that computer is connected with more than 10,000 sensors and the camera. That camera, when that car is running on the road, is collecting the images, and the sensors are also collecting the data, and then it is fed to the computer, which is placed on the car, and then that deep neural network will process all these inputs and predict something, and it will then activate the actuators, which will autonomously press the brakes or turn your car to the right or left based on what are the signals and everything, right? So now when they train it in the US, you can imagine that US people, they usually follow rules. Okay, so if there is a red signal, it is expected that pedestrian should stop by the road, and he should allow cars to go, and once the signal is green, they should pass. But since I'm from Pune, I usually get access of many type of such people who are using their hands still to stop the car if there is a green signal, right? So imagine that when Tesla will start their operations where the deep neural network is trained, where if the signal is green, go. And in Pune, when there are lot of people who are using their hands and not the signals, you can imagine lot many accidents will happen. So the training happened in US and testing and operations in India is never going to work. Okay, so you need to develop your own Tesla car or own Tata Motors car, autonomous car, which is trained on the local data. So that is also one of the important factor when you want to structure your deep learning projects. And I mean, the severity of the life, the severity of the consequences is huge when you use deep learning in healthcare, deep learning in automobiles. Okay, so make sure that if you are doing something on those lines, you need to make sure that you are selecting proper development and test sets so that you can rely on those tests basically. Next thing is about human level performance, which I already told you that rather than comparing the accuracy of your model to 100 as a benchmark, you need to compare the accuracy of the model to Bayesian optimal error, where Bayesian optimal error is calculated by what max can be achievable by humans. Okay, so that's how you can evaluate the performance. Then the third thing which you need to take, what is human error, what is training error, and what is development error. Okay, so when you are taking into account human error, there is one more word which is called as avoidable bias. That avoidable bias is if there is enough bias with human performance, then not to worry on the bias which gets introduced in training error. So that we can say that we can avoid that bias because we are assuming that human error is quite enough. So not to worry on the bias which happened at the training cycle. Okay, so I mean, just on the slide we are just discussing couple, I mean 3 to 4 or 4 to 5 techniques, but such things, if I would like to disclose and I would like to explain in length, then there are 20 plus to 30 plus different mechanisms and techniques which we need to take into account when we want to deal with a particular solution and particular situation in structuring the machine learning project or deep learning project. Okay, so yeah, the last way, the most effective way to deal with the errors that you applied all hyperparameters, you apply all set of optimizations, and again you applied all type of techniques to reduce the errors, but still you cannot reduce the errors. So then in this case, the only thing which will help you is MS Excel. So you need to create an Excel sheet. In that Excel sheet, you need to create the headers like you can say the name of the example, then the properties in that image, the type of cat, what you think is missing in the image, what are your observations, and all those things you will place. Okay, and then you will pick the vertical where you got maximum number of entries or maximum number of errors, and then those observations you will see, and you will try to use some algorithm or manual solution to avoid that particular problem. Okay, so this type of error analysis is a common practice in industry when we work on real-time projects. Okay, so this is how we do error analysis in when everything went wrong. So the next thing is about uh, the mismatch between train and development or test data. Okay, so when, let us say, when you splitted the data into train, development, and test for your deep neural network architecture, and I mean, that particular partitioning introduces huge error as output. Okay, so there are a couple of ways to sort this particular case out. One is, rather than taking the fixed, I would say, partitions of train, development, and test, what you can do is you can take a random shuffling, right? So for every training cycle, you will take random shuffling of train, test, train, and validation. So what will happen is that will give almost uniform distribution of training and validation data across the training cycles, okay, which helps you to reduce the validation error, and most probably your model will generalize well on the test data. Okay, so that is one of the way, which is random shuffling to avoid the mismatch between training versus development and test. Okay, so the second most important way, once you adopted this random shuffling way, is understanding the data mismatch. So how you are going to understand that data mismatch? For that, you basically need some uh, pre-processing techniques, pre-processing algorithms, which basically helps you to derive the statistical significance, correlation, covariance, and you can say the ED analysis from the data. And once you are sure enough that yes, the distributions, the correlations, the eigenvectors, the variance, all these things are set and they are consistent across train, development, and test. Okay, then most probably you can able to do that. Now you will say that why this is important, because this is a common practice in machine learning. Though it is a common practice in machine learning, when I saw different projects which academicians are doing, mostly they don't have that much of data, okay, which is required. So in a situation when you have a limited amount of data, then you need to apply a lot of pre-processing and data normalization. Okay, when the amount of data or volume of data is somewhere exceeding, you can say, 10,000 GB or 1 TB or two petabytes of data or exabytes of data, and continuously you are grabbing those scale of data from the APIs, and then you are feeding that into real time. In those industrial environments, this is something not needed, that you need to apply too much pre-processing onto that. But if amount of data is huge enough, you can directly feed the data to your neural network and no worries about pre-processing. Yeah. One more interesting fact about deep learning is transfer learning. So this is something that I learned deep neural network, and I'm passing on that information and knowledge to you. This is called as transfer learning. So rather than training your neural network from scratch every time, you please check, is there someone in market who open sourced their deep neural networks or pre-trained architectures on the similar type of data? So let us say you are building a cat classifier. What you will do, you will search online, cat classifier using deep learning. So you will get some Medium articles, okay? Then you will see what he has done, and you found that he have given the link to the GitHub. So you will go there and you will see, oh, he trained his CNN onto cat type of images. Then you will see what type of images are there. Luckily, he is Indian. and you are also Indian. So you will see that he collected the cat images from, let's say, Chennai, and you have the cat images from Pune. All right. So you see that by randomly verifying some cat images, you found that mostly the cats are same. So what you can do is, once someone trained the neural network, they found the weight values. Okay, so those weight values are the weight values which, if applied onto cat image, will give the classification label cat with 99% accuracy. This is what that person achieved. Now what you can do is, on your input data, you can, because when someone train the model, he will say model.save, and he will save that model into .pickle file. So that .pickle file contains the configuration and the weights. Okay, because configuration, he decided that how many layers, how many neurons, what should be the nonlinear activation function, was Sara configuration. So that saved model you need to download, and you need to load onto your current directory. Once you load that, run into Jupyter Notebook, and rather than giving a single training cycle, you can directly feed your image to that pre-trained architecture, and straight away it will predict there is a cat. This way of doing is called as transfer learning. So we are transferring the learning from one application to another application. Okay, so what basically we are transferring is, we are transferring the weights. So that is nothing but learning. So you can imagine your case, that what is learning. So when I see TV, I usually, in my early days, when in my childhood, when I see, let us say, a TV, I would have said that it is a slate, because it looks like a slate. But then my father told me that no, this is not slate. See, I am starting the TV, and you can see some channels, right? So I started reducing the weights. That if I see something like this, where there are display and there is something shown on the display, I will provide higher weights to TV as a label. Okay. And when I see some similar type of structure where someone is writing using pencil, I will give higher weights to a label which is called as slate. So this is what my experience is. Now already that pre-trained architecture got an experience, and that experience is stored in the weights. Those weights, if you use as is in your architecture, you can directly use that. Rather than doing a training, you can directly test. This type of methodology is called as transfer learning. It avoids your cost on the infrastructure, your cost on the data collection, your cost on the time, and whatever best practices are adopted, those bad practices you will get in your hand to utilize that. Okay, so this is nothing but transfer learning. So yeah, the next type of learning, which multitask learning. Okay, so what is multitask learning? Multitask learning is, at the same time, I want to label the pedestrian, the car, the road, the trees, the stones on the road, the wild animals on the road, right? So everything. Okay, so that type of learning is called as multitask learning, where you need to make a change in the last layer. So the last layer, the number of dimensions, the number of neurons in last layer will be the number of classes you want to detect. Okay, so let us say the number of classes you want to detect for your car, you want to develop autonomous car. So the classes are signals. So green, yellow, and red. Then zebra crossing. Then pedestrian. Then you can say the other cars, right? let's say these 6 classes are there. So the output dimension will be 6, and your deep neural network will provide you 6 probabilities. Okay, and you will have a one hot encoding vector at the end, which is your ground truth, which tells 1 to the class which is available in the image and 0 for the remaining one. And then you will calculate the softmax loss for the whole, and then you will back propagate. And same you will do for every class which you want to detect. So this type of learning, where you want to learn more than one class in a given input, is called as multitask learning. So that multitask learning can be implemented by making some slight changes in the cost function. So the cost function will become now 1 upon m, so average across all m examples, sum over all m. If the number of classes are 4, then sum over 4, so y log y hat plus 1 minus y log 1 minus y hat. Okay, so that loss you are calculating for sum over all 4 classes. So you are calculating that loss for every 4 classes, and the objective function is to minimize the whole loss across all the classes and across all the examples. It means when you minimize that whole loss, you can able to detect any object out of this 4 with highest accuracy. Okay, yeah. So this is called as multitask learning. And the last one is end-to-end learning, where we won't make any change in between. So there is no feature engineering in between. We will directly provide the input and we are expecting the output. So that is something called as end-to-end learning, which nowadays also called as AutoML or Auto Deep Learning. Okay, so these are some of the variants which are available in the market if you want to use them to do your task. Okay, so I think this is 350. Okay, so let me see. Okay, any questions? Let me take some 5-10 minutes break in questions, and then we will continue. Chaya madam, what is the procedure?
Ask questions if the students are participants are having any questions, and we will answer that question.
The most important thing is, in 2 situations there will be questions. The one is if you understand everything or you don't understand anything. so I'm expecting questions. Yeah.
Just we will already have, if any participants, if any questions, you can put in.
Good afternoon. May I?
Yeah, please go ahead.
Okay. Good afternoon, sir. The session was very nice.
Thanks.
Sir, basically I come from mechanical background, so I am a beginner in this domain. So my question is data augmentation for statistical features is possible?
Statistical features, what do you want to refer at?
Mean, mode, median, skewness, kurtosis. These are the statistical features which come in the numerical format, number format. So not in the image format, just that we have discussed regarding CNN, that image we take.
Yes.
So instead of image sensor, if we have data in the form of numbers that are statistical features, mean, mode, median, skewness, kurtosis, etc. So is the data augmentation is possible for statistical features?
Yes, it's possible.
So how, which method, which neural network, or what?
So for that, you need to understand GAN, that is Generative Adversarial Network, which is one of the most advanced network, which helps you to understand the inner embeddings of the distributions. Let's say you are saying that in terms of numbers, and then it will give you some approximations, and those approximations you can treat as one more sample of the data. So you need to learn GAN.
Okay. So GAN is possible with what Python, Excel?
Yeah, this is the extended, I mean, more advanced neural network, generative adversarial neural network, whose task is basically understanding the inner approximations in the data and then represent that onto some other dimensions, which you expect it want to. So it is a
Okay.
Python-based deep neural network. You can, even there is a package available, you can directly use that and annotate your data.
Okay, sir. Okay. Thank you. Thank you so much.
Thanks. Someone is doing PhD in deep learning?
Yes, sir.
Okay, you are doing PhD?
Yes, sir.
Oh, nice.
Thank you, sir.
Your voice is not audible, ma'am. I think. I think. Let me check chat. Okay, all right. It seems nobody understood deep learning. That's why there are no questions. Fine. So, fine. See, the point is this topic is really vast. Every day there are more than 100 plus research papers released, and I'm trying to keep myself on that pace by reading at least 1 to 2. But that's the only way you can keep yourself consistent on the track. But this is amazing that every day there are extensions, advances, modifications are going on, and the 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 topic or the concepts which you are learning, they are basic concepts. I mean, nowadays people understand this, but if you want to really get into deep learning, I think the only way is reading the research papers every day and understanding what's going on, how researchers are making modifications, uh, and using that small modifications in the maths, what is achievable, what is not achievable. So once you do that for an year, then you can set up the hypothesis that yes, I understood the way things are going. So you can put up your own theory. This is how things should go, rather than having in the disjoint way that someone is telling you to do this and you are doing that without knowing why you are doing and what you are doing, right? So yeah, so this is expected in deep learning. I don't know about other domains, but deep learning expects this type of uh, working. Okay, so yeah, uh, so it's almost 4. Whether audience is still ready to go with for half an hour, or should we quit? Hannah, your voice is not audible. I don't know. Uh, so mammogram classification. So there is one question: which are defined models in suitable for